بأحمر صح؟ Now I will start to continue our lectures for today. I know it's a huge amount, but as I told you, we are hectic on time. So I will continue, inshallah, today with continuity and differentiality. Hopefully we will be able to finish the amount that I want to finish with you. And at the worst case scenario, I've already uploaded most of the lectures on the YouTube. Okay? So I will start from the continuity of a function. So Ms. Sulai, it's really very simple to prove that the function is continuous. In one dimension, you have three conditions. Those are the keys to understand the continuity. The three conditions are by logic, that the value of the function at the point exists and defined. What's the meaning of defined? You can find it on the x-axis, or it has a meaning. So first of all, the definition exists, or the function exists. Number two, the limit of x tends to a already exists. Number three, both the definition and the limit are equal to each other. So how many conditions? Three of them. The function is defined, first step. The limit exists, second step. And the both of them are equal to each other. In this case, your function is continuous at this point, which is point A. How to study the continuity within a set or within an interval? You have to be sure that those three conditions exist at each point within the set. Okay, once we go to functions in multi-variables or with several variables, then we will move to continuity of two variables and more. If I'm talking about limits in two variables, okay, the definition, I will go with the limits using the definition, but just only with a slight difference. So if I have D belongs to the set of R squared, X naught, Y naught, and I'm having the limit of f of xy should equal to the definition. If you remember, I had three conditions. What were the three conditions? The limit, the value of the function exists, which is f x naught, y naught. Number two, the limit exists, which means limit xy, f of xy. The third condition, they are both equal to each other. So in several variables, all I have to do is to prove that the limit of the function equal the definition. That's it. How to prove it, Ziad? In order to prove this, using the general definition, I will consider epsilon greater than 0, which leads to deltas greater than 0, such that for every xy minus the origin, delta or delta will lead to f of xy, not minus any value, minus the specific value of the function at this point. So the difference between the continuity and the limit, that f of xy minus L should exist. But in continuity, f of xy minus f at x naught, y naught. Yani the value of the limit equal the value of the function at this point. Okay? Similar steps will be followed exactly as dealing with the limits as we saw previously. So, this is exactly as I told you. This is to prove that f of x minus the value of the function at a is less than epsilon. So it exists and everything is okay. Also for you, if it is required to choose a correct answer in some multiple choice questions, this statement is really very important. If a belongs to the, and it is an isolated point, the function is continuous at point A. So if you have an isolated point, the function will be continuous at this point, okay? Also, if A belongs to an accumulation point, then f is continuous in A, if and only f, the limit exists and it's equal to f of A, which is mainly the main definition. This is the condition in a set. In order to have a function continuous in a set, it has to be continuous at each point belongs to this set, okay? Once more, also, if you have two functions are continuous, their addition or subtraction, their multiplication, their division is continuous, except when the denominator is equal to 0. It's not going to be defined. So once more, if you have two functions, Mr. Ziad, they are going to be, and they are continuous mainly, their addition, subtraction, multiplication, division is also continuous. Okay, very good. This part is important, Ms. Fatin. This is an extension of continuity. In some cases, I would find the function. But this function, the limit doesn't exist, okay, for this function. But I'm sorry, the value of the function at this point is not defined. But I can find the limit. And the limit exists. So I can generate a new function, okay, at this point, putting a condition to make the function continuous. What I want to say, if for example, I have f of x equal to 3 over x. This function is continuous. صح? This is continuous function. Why it's continuous function? Because if you try to make a substitution at x equal to 1, at x equal to 2, the value of the limit and the value of the function will be equal to each other. But if you try to discuss the continuity of this function at the origin, we can't do that. Why? Because the limit, or I'm sorry, at infinity, we can't do that. But I can speculate and put conditions in order to do this continuity or to discuss this continuity. If I'm talking about the continuity at the origin, Ms. Fatin, is the function defined at the origin? No. The 3 over x. No. Can you find the value of 3 over 0? No. But I can do something very nice. I can say that f of x is equal to 3 over x, while x doesn't equal to 0. But when x is equal to 0, I can find a certain value, okay, in order to validate this condition. I will say, at x equal to 0, the value of the function is going to equal to 1. You understand what I'm saying? In this way, I will connect the function and it will be continuous in other examples. So, for example, I can say that f of x is equal to 3x plus 4, while x is greater than or equal to 1. And when x is less than 1, it is x plus k. I want you to find the value of k for which this function is continuous. What are you going to do? I will try to find the limit of the function from above, which is going to be 3 times 1 plus 4, which is 7. Okay? I need the same value here. So I need x plus k should equal to 7. In this case, when x is equal to 1, k will equal to 6. So if k is equal to 6, this function is continuous. The same values, then the function at the first branch and the second branch will be equal to each other. Are you with me? This is how to extend the continuity to a certain function. I will show it to you in problems just within the coming problem directly. This is really very important. It's called the extension of a function by continuity. Okay? So let's discuss, and this is how it's gonna be. This is the value of f of x when x under certain condition. Then put the limit equal to g of x when you are completing this condition. So show that the function x squared minus y squared over the root of x squared plus y squared, okay, when x tends to the origin is continuous. Or extend by extendable continuity, or extend the conditions to change this function to be continuous at the origin. Before starting this problem, I will try in this problem to solve it by more than one method. To solve the limit part, in order to review how to go through Euler, how to go through the Cauchy substitution, and then finally I will show you how to extend the continuity of this function. So at the time being, I want to see if the limit is equal to the origin. To show that it's extendable by continuity to the origin, we must show that this function, which is the limit of xy tends to x squared minus y squared over the root, already exists and to find the value of L, and to find the value of this function. How to extend it? I will do it this way. I will say if x, y doesn't equal to the origin, I will use this function. When it's equal to the origin, I will put the limit, which is the limit. Okay? So in this case, the definition will equal to the limit, so the function is going to be continuous. This is the bottom idea. Okay, let's start by using polar coordinates. This is one of the methods of the limits that we discussed earlier this morning. In order to do polar, I will have to change every x by r cosine theta and every y by r sine theta. Let's do this. So I will get back to my problem, replacing x and y by r cosine theta, r sine theta. Okay, very good. So, which means the root of x squared plus y squared is gonna equal to r. Once you start to do this, this is gonna be r cosine theta to the power of 2 minus r sine theta to the power of 2 divided by r, as you can see. I can eliminate r with the power. So I will have r times cosine square theta minus sine square theta. In this case, if I took limit r tends to 0, this is gonna be a constant. So 0 times this value, the result will be 0. Now I know that the limit exists and the limit should equal to 0. If I want to extend, if I want to extend the continuity of this function, I will say that this function is equal to x squared minus y squared over root x squared plus y squared everywhere, but not at xy doesn't equal to the origin. If xy is equal to the origin, I will put L equal to 0. This is how to extend. So L is the limit. Okay? That's the new function which is going to be continuous. I get over the value that I can't substitute with the origin. Okay. Because of also he told you that cosine square minus sine square is bounded and the r tends to 0. So using the squares theory, the limit is going to equal to 0, exactly as we mentioned in this slide. So the value of the function is equal to 0. This gives a new function, f of xy, that's continuous at the origin. As I told you, all I have to do is just to put these values equal to 0 in order to be equal to the limit. Now I have the limit equal to the value of the function. It's continuous. Ms. Fatin, I will do once more this problem. I will solve it again, but not with the polar substitution. I will solve it with r and theta. So once more, okay, I will go. This is the definition, and I want to find the value, but I will do it this time using epsilon and the delta. How to use epsilon delta? I will start once more. Add the limit xy tends to 0 and such that it can be extended by continuity, blah, blah, blah. I will say for every epsilon greater than 0, there exists delta greater than 0. I will start from this part, which is x squared minus y squared divided by root of x squared plus y squared. Of course, this part can be rewritten as the following. Instead of having x squared minus y squared, I can make it x squared minus y squared. And then I can replace this guy by x squared plus y squared. So I can diminish this value with r. And so I can find that this value is equal to 2r. In this manner, if I have epsilon greater than 0, then I can find delta greater than 0 with the same results exactly. بصوا. I can write for every epsilon greater than 0, there exists delta greater than 0. Okay, very good. Such that I will have that x squared minus y squared divided by the root of x squared plus y squared minus 0, which is not going to be written. But I know this value is equal to x squared minus y squared divided by the root of x squared plus y squared, which is less than or equal to the absolute of x squared plus y squared divided by the root of x squared plus y squared. I used one of the inequalities that I've already introduced it in the previous session, okay? Once more, I can replace this guy. Instead of having x squared plus y squared, I can replace it with r squared. So it's less than r squared over r, which means r. That's r greater than 0, which leads to that it is less than epsilon. So using this definition, now I am sure that if I use delta is equal to epsilon, or even epsilon over 2 in the other proof, then your value is correct. Or once epsilon is greater than 0, according to this relation, delta is greater than 0. Now the limit exists, this limit exists. So the limit of x and y tends to the origin 4x squared minus y squared divided by x squared plus y squared is equal to 0. Now I can write a new function of an x and y, which is gonna be x squared minus y squared divided by the root of x squared plus y squared, when xy, okay, doesn't equal to the origin, but when x and y is equal to the origin, I will put the value of the function equal to the limit introduced, which is 0. In this manner, I can extend the continuity of the function at the origin, exactly as I told you previously, okay? So once more, I can go through the main steps as you can see. So once more, at the limit xy tends to 0, I can once more use the definition that for epsilon greater than 0, there is delta greater than 0, and I have the absolute of xy, x squared minus y squared over root of x squared plus y squared. I can do it polar, I can use the absolute results, I can use every result, every relation that I've introduced previously with you. There are plenty of ways. Okay, now I've proved, I've reached that it's equal to 2r, and 2r is less than epsilon, which means for epsilon greater than 0, I will have delta greater than 0. In this case, or in this value, it proves that there is an open ball with the difference, so the limit existence is equal to 0. Now I can extend the value of the function. Here is the value of the function. That's the function, and that's n. In this case, n is equal to 0, then the function is continuous. This is how to extend the continuity. Stop. From the beginning, no. From the beginning, I mean stop at the time being, but I want you to follow up with me. From the beginning of our course, we have introduced what are the functions in one variable and in several variables. This is number one. After going through this issue, we spoke about various types of coordinate systems, which are Cartesian, polar in 2 dimensions, in 3 dimensions, spherical, cylindrical coordinates. Now I've mastered the coordinates and the relations connecting them together with a huge amount of problems. Okay, I have the functions, I have the coordinate systems. I've used both of these two types with the help of parametric representation of complicated shapes, either functions or graphs or surfaces or whatever. This was the topic of the previous session. Okay, with all of this information, we went today through the limits. And we understood the difference between the limits in one direction or in one variable and the limits in multivariables. Okay? Using the 3 methods, the general, the iterated, the directed method. Connecting with the limits, we did go through the continuity. And we knew that continuity is exactly like limit, but just only with one condition, that the value of the limit should equal to the value of the function. Done with it. Now I'm going to go through differentiability. How to study differentiability. The study of differentiability, Ms. Fatin, is the study of the limit, but using a specific law. So in differentiability or in derivative, I will talk about derivative for functions in one variable. The derivative of functions in one variable, which is f dash, sometimes we symbolize it, as you know, Mr. Farid by df by dx, which is the change in the function, in the output, relative to the change in the input. And it's equal to f dash at certain point. It's the limit, the difference in the output by the difference in the input. And also, for a small arbitrary change in the input, I can write the limit in this way, which is the famous limit of the derivative of a function. So I can say that y dash or dy by dx, or the limit of h tends to 0 of f of a plus h minus f of a over h. If you remark, it's a limit. In a similar manner, I can use the same method in multivariable functions. At the time being, now I know the definition of the derivative in one dimension. So once more, provides an important information about the behavior of f at the neighborhood of certain function. It will help you to know the monotonicity of f, which means the derivative will help you to know if the function is increasing, if the function is decreasing, or what. And also it will help you to find the equation of a tangent line at any point. That's mainly the main uses of the derivative. By the idea, the tangent you have to need for at any point is equal to f of a plus f dash a times x minus a. That's the equation of a tangent by knowing the derivative, okay? And also, if you remark, I can reorder this equation and it will come to this one. Just, it will be f of x minus f of a divided x minus a, which is f dash a. This is why the equation of the tangent to a curve is very connected to the definition, which is the difference in the output by the difference in the input. Okay, once more, that's the first order approximation, which is f of x is approximately equal to f of a plus f dash at certain point times x minus a. I can use this relation to approximate the value of a function in the neighborhood of a certain point. Okay? This is the approximation. For the partial derivative of two variables. In one variable, we use total derivative because you just only have one variable. But in more than one variable, I will have to specify which direction I'm going to differentiate with respect to. This is why in xy, I will have to tell everybody that I'm differentiating with respect to x or differentiating with respect to y. From here it comes the partial derivative idea. If I'm in 3 dimension, I will have partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. If I am in n variables, I can differentiate n times. Differentiating the function with respect to x1, differentiating the function with respect to x2, with respect to x3, with respect to x4, up to xn. شباب انتوا فاهمين اقول ايه؟ فريد انت فاهم متابعني؟ طيب. Guys, if I have y equal to sine of x, can you get me the first derivative? Ha!
Cosine x.
Y dash is gonna equal to dy, صح? By dx, and it's equal to cosine of x. تمام? Okay, if I have z equal to a sine of an x times y, I want to differentiate. The question is, are you going to differentiate with respect to x or with respect to y? Because I have more than one variable. So in this case, I will know that there is z sub x or partial z partial x. معايا فريد? In this way, I will differentiate only, I will consider the variable x. And for y, I will treat it as a constant. Please. Also, in a similar manner, I can differentiate with respect to y. Let's first differentiate with respect to x. If I'm differentiating with respect to x, then I will differentiate sine, which is cosine the angle. Am I right? Mm-hmm. Then I will differentiate the value of x, which is 1 times y. Here we go. So I'm treating y as a constant. معايا Mr. Farid? Okay, once more. I want to differentiate فاتن z sub y. In this case, I will consider the variable is y and the x is a constant. Let's do the derivative. معايا زياد? It's gonna be partial z partial y, which is gonna be differentiate the sign, which is gonna be cosine of an x y. Then I will differentiate with respect to y, considering x as a constant. Y derivative is 1 times x, so the value is x. So in this case, I've differentiated the function with respect to x, then with respect to y. What if the function is in 4 variables? What if I'm dealing with L, which is x, y, z, and t? It's a function in how many variables? 4 variables. Now I can differentiate L with respect to x, or differentiate L with respect to y, or differentiate L with respect to z, or differentiate L with respect to t, and so on. Okay? So, bottom line, the partial derivatives will be needed if you are dealing with functions in several variables. The total derivative will be needed if you are dealing with a function in how many variables? 1 variable. Okay? So, how to introduce the limit law in case of partial derivatives? In partial derivatives, the limit law is stating that if I want to get partial f, partial x, if it is in xy, it's gonna be the limit of x and y, or a and b, tends to the origin, okay, of the function f of x plus h and y minus f of x and y divided by h. This is the law. Remark, I'm differentiating with respect to x. So I put the increment in the x direction. If I am differentiating with respect to y, I will put the increment in the y part, and so on. معايا يا شباب? Okay, that's the definition of how to use the partial derivatives. طبعا, it's stated here, partial derivatives over 2 variable functions. Let d belongs to r squared, a and b belongs to the interior of the interval of d. And so, in this case, if I want to get phi dash, it's gonna be in the direction of the x, so it's gonna be f of a plus h and b minus f of ab over h. Remark the h is in the x direction. If I want to get y, which is in the other direction, I will put k in the y direction, and it will be a plus b plus k minus f of ab over k, and I'm taking the limit of k tends to 0. That's the derivative, or that's how to use the limit in the x direction or in the y direction. Okay, and that's an interpretation exactly like finding the slope of the function but in the x direction, finding the slope of the tangent to the function but in the y direction. That's the geometric interpretation of both of them. So, once more, this is partial f, partial x, limit h tends to 0. As you remarked, for x, it is h in the x direction. For y, it will be anything, h or k or whatever, but in the y coordinate, okay? Here, for example, I want you to calculate the first order partial derivatives of this function, which is defined everywhere. It's extended, this function. It is extendable to continuity. Why? Because the function is not defined at the origin. But I found a value to input in the case of the origin, if you remark. This is a piecewise function. Everywhere except the origin, this is the value. But at the origin, consider the function is equal to 0. Now extended to by continuity. Are you with me? Okay. Now, let's find the derivative as I told you. Let's find the derivative with respect to x. With respect to x at the origin. So I am using limit that h tends to 0 for f of x plus h and y minus f of x and y. In this case, my x and y are zeros. So it's an f of 0 plus h and 0 minus f the origin. F at the origin is equal to 0. from the definition. F of 0 plus h at 0, which means I will replace y by 0, okay, times I will replace x by 0 and h, and will be divided, all of this will be divided by h square plus 0 square, h square plus 0 square. But before we're going further, this is 0 times something, so the value of the limit is equal to 0. So actually I'm making the substitution, but since you have 0 in the denominator, the value will equal to 0. You will see it in the coming step. So once more, that's the x derivative, that's the y derivative, is going to be similar. Both of them are equal to 0. So this is the function. Since at the origin x is equal to y, the function is defined at the 0. So once you try to make the substitution, either in both ways, taking x is equal to 0 or y equal to 0, the value of the function is going to equal to 0, as I told you. In a similar manner, if you are doing for the second direction, it will be also equal to 0 for the same direction. So compute f of, so the limit existence equal to 0. For fy, it will be exactly the same. It will be equal to 0 also. Same way, it will be 0 and h minus 0 over h. Those are the values of the function at the origin. معايا Soleil? Are you still following me or no? Do you want me to repeat it from the beginning? Okay? Repeat or no? Okay. Then the value of the function is already existence equal to 0. So both of the partial derivatives at the origin is equal to 0 for this function, as you can see. This is the first two derivatives at the origin is equal to 0. For the partial derivatives and continuity, in case of n equal to 1, if dash exists, then f is continuous. In case of n equal to the existence, خلي بالك يا فاتن ده ممكن يجيب multiple choice. يعني in one dimension, لو الفانكشن differentiable, it is continuous. Okay? Did you find the lady? Didn't you ask anyone else? ما سألتش حد تاني؟
مكتوب 1 hour.
هترجع بعد 1 hour؟ Okay, in the case of n equal to 2, the existence of first order partial derivative at point A doesn't guarantee the continuity of A at a point. بص زياد, in one dimension, if the function is differentiable, it is continuous. But in two dimension, لا. يبقى تاني, in one dimension, in multi-variable functions. In one dimension, if it is differentiable, it is continuous. But multivariable functions, no, it's not guaranteed. In case of n is equal to 2 and more, the existence of first order partial derivative at a point doesn't guarantee the continuity at this point. Partial derivatives of n variable functions, it will be a generalization to what exactly to the previous law. So if I have n variables, I want to do xj, so all the variables will be the same except at xj. I will have aj plus h. Taking h tends to 0 minus the value of the function. So it's exactly the same law. If you remark, this is for partial f, partial x, it was limit h tends to 0 of f of x, I'm in the x direction, so it's gonna be 0 plus h, and y exist is equal to 0, divided by h minus f at 0 and 0. If I'm not approaching the origin for an a and b, this is gonna be a plus h and the b, and this is gonna be a and the b, and the h tends to 0. It's the exact same definition. But here I have just only two variables, but here it's a generalization of the idea of the law. So that's mainly the main law that I can use. Partial derivatives of some product multiplication, it's exactly all the laws with the derivative. Do you remember the derivative laws? Do you remember the main derivative laws? Okay, its derivative can be distributed on sum or difference. Derivative of two functions multiplying each other, get the derivative of the first function times the second, plus the derivative of the second function times the first. If I have two functions divided with each other, I will square the denominator, find the derivative of the denominator times the denominator minus vice versa. All the laws of the derivative are going to be applied. But just only with one difference. You will have to determine the variable that I'm differentiating with respect to. So if I'm differentiating with respect to x, I will consider y a constant. If I'm differentiating with respect to y, I will consider x as a constant, and so on. This is actually what being stated here. This is the addition, the multiplication, as I told you. This is the division, okay? That's the division law, as I told you. Square the denominator, find the derivative of the denominator times the denominator minus vice versa, and so on. Second order partial derivatives. In the second order partial derivatives, it is the derivative of the first order, exactly like functions in one variable. So once more, for an example, Ms. Fatin, try to solve this problem with me. I'm sorry that I'm bothering you, but this is important. As 4xy plus y squared. I want to differentiate this function with respect to x. So it's going to be z sub x, which means partial z, partial x. How to do it, Ms. Sulay? I will differentiate with respect to x, treating y as a constant. So it's going to be a 2 of an x. Then differentiating x, it's going to be 1 times 4y. So it's going to be 4y. Differentiating y, which is equal to 0. If I want to get partial z, partial y, Farid, the first one, it's going to be a constant. So the derivative is equal to 0. I'm differentiating with respect to y. So it's going to be 1 times 4 of x. I'm differentiating with respect to y, which is going to be 2y. This is the first derivative. If I want to do the second derivative, in the second derivative, I can differentiate this function either with respect to x, so it's going to be partial 2z, partial x squared, which is going to be differentiate the first derivative with respect to x once more, it's going to be 2. And also, I can differentiate it with respect to y. يبقى ده with respect to x. If I want to differentiate with respect to y, then it's going to be partial 2z, partial of x, partial y, which means that I'm going to